fantastic argument for a flat stationary Earth.
Absolutely. And Bob, what did you think? Did you see the couple videos that everybody did making fun of not a professor for him being grossly wrong in the 8 inches per mile squared?
Yeah, in fact, somebody wrote me a letter on that, and I said, you got to be kidding me. And except this guy was saying that it was something else completely different. It was kind of like one of those Dan the Waterman deals, you know. Maybe it was him in disguise. I don't know. But yeah, when I saw that, and he's sitting there saying, "Oh, you didn't even try it. You didn't even try it out or look it up or anything like that." And it's exactly what he didn't do,
right?
Or
Exactly.
he would have known.
Exactly. If I could find the TikTok, I'll play it. But somebody did a great TikTok, and this is why people hating on TikTok. I'm like, look, nobody else is doing that kind of work, which was simply taking what is the name of that guy? I Can Science That. He did a video.
I Can Science That. Yeah.
He's a Glober, but he at least is honest enough to call people out that are Globers when they make gross mistakes, which is what not a professor did. And so some guy made a TikTok of the combination of what Professor Dave was saying and then what I Can Science That was saying, which was him showing that you can absolutely do all the things that the professor says we cannot do.
Mm-hmm.
If I can find
it. And Dave's was really good too. I'm sitting there looking for it too, but I didn't see the TikTok on it. I don't usually check out TikTok that much.
And what did Dave? Dave did one. Did he ever release it? I thought it was sitting on private for a while.
No, it's released, and it was just the one that was showing, Dave getting it all wrong. Pretty much like everybody else did, unless that's a copy of the TikTok thing. I don't know.
I don't either. No, I'm not finding it. I thought I had it in here, but anyway, it's great to see people doing that. We need more people doing that. You could take clips, mix them together, and again, it's not even. I wouldn't even consider it difficult what you're doing. Oh, here it is. It is right here, I think. I'll have you watch this TikTok because it's. Wait, is this it? Hold on, let me see. This might be it. Oh, no, I have sound on.
Good. 8 inches per mile squared. It is time to end a globe talking point.
You can't hear that, Bob?
Good.
Tell me if there's an echo if I try and turn it on.
8 inches per mile squared is not a valid way to measure
Okay,
Earth's curvature.
Go ahead and say something.
8 inches per mile squared. None of you have any idea what this means. You can't derive it. You can't calculate anything.
Yeah, it echoes, but it's listenable.
Okay, let's just listen to it.
You can't tell me anything about this.
I'll start it over for you.
It is time to end a globe talking point for good. 8 inches per mile squared is not a valid way to measure Earth's curvature. 8 inches per mile squared. None of you have any idea what this means. You can't derive it. You can't calculate anything with it. You can't make a prediction with it. You can't tell me anything about this value at all.
I like that one. We can't make a prediction with it. Let me see. Austin, let me have you make a prediction. How many inches do you think the Earth curves in 1 mile?
8 inches.
Wow, that was weird. You made a prediction with that 8 inches per mile squared?
Welcome to I Can Science That, where we do honest investigations of everyday science. Anyone who is a glober, if you're out there trying to dunk on flatties, then this video is for you. I'm going to derive the actual formula for the drop rate, the formula that NASA would actually use. So there you have it. I have now derived 4 different versions of the drop equation compare to the 8 inches per mile squared estimate. I've got the distances in miles, and all of the drop distances I have written in feet. If you're 1 mile away, the 8 inches per mile squared will give you 8 inches, and that comes out to 2/3 of a foot. So that's that. How does that compare to our actual values? Here's the actual amount of drop distance according to these different equations, and we can see that's super close. I mean, that's within tiny fractions of a distance. And so at 1 mile, it's fine. How far? Let's go 5 miles. We'll go 5 miles. And we'll see.
Notice the 8 inches per mile squared actually undercuts.
Here's the approximation.
Gives less curve.
Pretty darn good. It's 100th of a foot is how far off that is. At 10 miles, the drop is still pretty good. Look at that.
You can't calculate anything with it. If you understood math, you would immediately see that this squared on miles is totally out of place. That's because this is a parabolic approximation. This is for doing calculations with a parabola. As you can see, the Earth is not shaped like this.
Like, that's not a. How is that? Is that the only parabola? Is that can't be extended, can't be bent out or anything? It's only this thing here. He just lowers this shape down on the Earth. Earth's not shaped like that. No, it's not.
It's for doing calculations with a parabola. As you can see, the Earth is not shaped like this.
So what if we're doing like a longer observation? We're going to go out further. Let's go out to 50 miles. So out at 50 miles, the actual value is there, and depending on which method you use, it's
Again, the 8 inches per mile squared airs on the side of the globe.
Not even a foot, half a foot. From this one, based on arc length, which is my favorite, I'm off by like half a foot.
You can't calculate anything with it.
Over 50 miles. I'm going to say that's a pretty good estimate. If 50 miles away you're only off by half a foot, that's pretty good. I'll accept that.
Well, I'm sorry, friends. Those people are doing incorrect math, or lying, or both.
Or neither.
You're counting on the fact that you won't do any math at all to check up on them.
That's what Bob's talking about. Is this guy just said, you're counting on the fact that you won't do any math at all to check up on them. And the one person who didn't do any math to check up on it was Professor Dave. That's hilarious.
Let's push it now. Let's push it out to 100 miles. Surely this approximation is no good at 100 miles. Here we go. The actual value, 6668 feet. And the estimated value, 6667 feet. We are now off by, oh my gosh, it's over a foot. At 100 miles, it's off by a foot. That is a darn good estimate.
Wow.
8 inches per mile squared is not a valid way to measure Earth's curvature.
So yeah, if somebody is telling you that estimate only holds over short distances, that estimate is shockingly good. Okay, but that's still only 100 miles. Let's go nuts. At 1,000 miles, here's our estimate based on 8 inches per mile squared. And here are our actual values depending on how we sliced it. I think you'll find that's still pretty decent. How decent is it? I've made a little chart. Let's cut away to that now, and I will show a graph of what we found, and we'll see our 8 inches per mile squared sitting right in here, and all the way out to 1,000 miles. This is a pretty good approximation. 1,000 miles, maybe that's not far enough. Let's push it. Let's see what happens if we just go all out. And this is what we get. Interesting thing for me here is that the horizontal length method and the arc length method diverge by more than the arc length method does against the 8 inches per mile squared method. The takeaway here that was absolutely eye-opening for me is that the 8 inches per mile squared estimate is really, really good.
Well, I'm sorry, friends. Those people are doing incorrect math, or lying, or both. But maybe a portion of you will have the courage to accept that you've fallen for a hoax. It's not that big a deal. Many of us have fallen for hoaxes or been manipulated at one time or another, myself included. Just admit that to yourself and walk away.
Anyway, not a professor. Again, blowing his shit in the bed. What are you gonna do? Shitting the bed. All right. Oh, you guys want that down. That's why you don't want that.
Exactly. And one other thing, I think I'm sharing my screen, Jaron.
Okay.
Can you see that?
Do I have to click on something nowadays?
The
new.
Let me make sure I've got the right thing up here.
I just see a black screen. Anybody else?
All right. Let me say stop sharing. I'll try it again. Confirm stop sharing.
Kyle's
share
there.
screen.
Hi, Kyle.
Hey, Kyle.
Welcome.
Hey there. Good to hear from y'all. Good to be back.
Awesome. Cool. Okay. How about now? Can
Now
you
I see it. Yep.
All right. So now the one thing that he didn't include is these two methodologies. Now he said he put his 4 methodologies on there that he liked. The Sagitta is the one that Kirk did it with. And then, of course, there's the AutoCAD calculation as well. And I just think that it's super interesting that the 8 inches per mile squared turned out to be almost a precise medium for all of the other 6 figures, right? So just because they've used the actual so-called, correct calculations, they didn't agree with each other, right? They disagreed with each other, which also disagreed with the Sagitta, which also disagreed with AutoCAD. But when you look at them and average them all out, the 8 inches per mile squared appears to be the most accurate.
Yeah, up to 1,000 miles for sure, and you'll never need more than that when you're just doing measurements because you can't see that far. So
that's right, and we're never going to go over 1,000. I mean, yeah.
And that is where, that's where they're all lost. Is they say that we're doing it for the globe, but we're not. We're doing it for the section of the arc that you can see, and it's spot on for this section of the arc. And why wouldn't you use the simplest mathematical? I mean, why would you go for the most complicated formula you can get when doing for a section of an arc? You would pick, be it a globe, be it a, any way you're looking at it, you would pick the section of the arc for accuracy and use the easiest formulation. That's common sense.
Here's the problem with these guys, and I consider them like Pinocchio, right? I think Pinocchio is a good description because Pinocchio is not a real boy. He's a wooden boy, and he can't think for himself, and he can't do whatever he wants. He doesn't have his own beliefs because he's controlled by a puppeteer. He's a puppet. And that's what these guys are. They're all Pinocchio. They're not real boys. They don't have real thoughts. They don't have real beliefs. So when you have something like the 8 inches per mile squared, it was never taught to Professor Dave. So he thinks because it was never taught in school, it must be wrong. So he doesn't even have to look into it because it's not what he's been sold as his beliefs. This is why when they bring up transgenderism or when they bring up the vaccine or anything, that you already know what their position is because they don't take positions. They don't make their beliefs known. They don't have beliefs of their own. Their beliefs are given to them from above. So it's just like Pinocchio. And, if you think about Pinocchio, how does he become a real boy? Well, he finally decides to trust his own science, his conscience, and to listen to that inner voice. And once you do that, the inner voice's name was Jiminy Cricket, which is pretty amazing that its initials are JC. But once you listen to that inner voice and you start following it, that's when you get to become a real boy, although I wouldn't hold my breath for any of these guys to become real anytime soon.
What I see here is when Rowbotham picked this equation, it was because it gives the globe the benefit of the doubt over all the other equations. This is the one that curves the least. This is what I do all the time when I'm testing something or this. I test it to the minimum, and that's what I'm testing.
Right, or you always
just want
give
to
the
see
globe
if it matches the minimum.
That's why when we do distance measurements or something, and we are 12 miles, so take it at 10. So you're always giving them the benefit of the doubt.
Exactly.
But when we're talking about fractions of an inch to maybe a few inches to less than a foot,
right?
Up to 1,000 miles, what difference does it make? It's pointless. They're all right in the ballpark with each other. So now we've got it verified through the 4 that I Can Science that did, through the Sagitta, through AutoCAD's, computer-aided drafting calculations that are built into it, right? And that's one of the last things I said to that guy that wrote me the email is, why don't you go ahead and write AutoCAD and tell them how they've got the curvature formula all wrong? They could probably use a good laugh,
Really.
It's absurd.
And the one thing that you want to just be careful of is just remember that you do have to take into account the observer's height and the height of the item above sea level. So, if you're just doing, we're just observing 10 miles, then you can do 10 times 10 times 8 and then divide that by 12 and you'll get your feet. But you can't just say then, now we're going to go out and look at that distance and make calculations on the items we see, because if you're 30 feet high or 50 feet high, that's going to change everything. So just remember to take those into account. The calculators usually will ask you your position. And I'm pretty sure this is correct. I should ran it by somebody, but I'm pretty sure it's correct, right? If the item that you're looking at is, say, 15 feet above sea level and you're 15 feet above sea level, you can just take yourself as 30 feet high, correct? Kyle, is that correct? Yeah. Okay. Thought so. It's the same. Ends up being the same.
Yeah. And so Yeah, absolutely true. And so anyway, our formula is good. And the thing that they do is they sit there, they're the ones that blatantly, openly cheat. They sit there and throw on this standard refraction variable on there. It's like, where the hell did that come from?
Oh, I know where it came from. I know where it came from. They went out and did observations a lot, assuming the globe. And then they had a predetermined window where they would only take observations or measurements within that window. And so when they get these observations that show the radius value would be way too big, they literally just disregard them entirely and throw them out. And then they get a weighted mean and average out how much off they still are after cheating, and it's roughly 15%. So they call that standard refraction.
Austin, how about this?